In your last few lectures, I have discussed the concept of stress in details. So today's lecture, I'll spend mainly to discuss the concept of strain tensor. Strain, the term you have already encountered in your first year mechanics, but probably you have learned what is the description of the engineering strain and the problems you have dealt with. Those are two-dimensional. So now in this lecture, we'll learn what is the strain tensor in the three-dimensional space. And before that, we'll spend time on discussing what is this motion, then what is deformation gradient tensor, displacement gradient tensor, then the definition of green strain tensor, and finally the infinitesimal strain tensor. So the concept discussed in this lecture will be applicable to both solid and fluid, and together we call them as a continuum body. But elasticity, mainly we relate the material as a solid material, but the concept discussed here will be applicable to both solid and fluid. So with that, let us start the discussion on motion. So to describe motion, I have to first explain this picture. So in this schematic diagram, let me position it very nicely first. And what you see here, there are two configurations highlighted. One is referred as the reference configuration, and another is termed as the current configuration. These are the two configuration of a continuum body. One is at the starting of the deformation, so at time t is equal to 0, or sometime this can be termed as t is equal to t0, or t0 often taken as 0. So at the initial position, or at the initial time, what is my configuration of the continuum body? That is termed as the reference configuration, or sometimes we call it as undeformed configuration. And then as the material deform, it takes many different configuration as it is shown in the middle. And finally, at time is equal to t, that is of our interest. So at that particular time, it take the configuration which is shown at the extreme right side. So this configuration is termed as the current configuration, or sometimes it is also known as the deformed configuration. So in this two configuration, if you see this picture, there are 2 points indicated. So the in the left side configuration, or in the reference configuration, as you see, a material body or a continuum body is consisted of n number of material points. So a dot indicating here is one such material point, which is denoted as x here. X actually denotes the position vector of that particular point P. And then after deformation, that same point P moves to a new position which is within that current configuration, and the position vector of that point P in this current configuration is termed as small x. So capital X is the position vector of point P in the reference configuration, whereas small x denotes the position vector of the same point P in the current configuration at time t is equal to t. Okay. All right. So this is what it is written here. I will not repeat. So the same material point moves from capital X position to small x in the current configuration. So with this discussion, now let me discuss these two description we have. One is called the material description, and another is the spatial description. The so-called material description, and the other name of this as this is as Lagrangian description. So this is a characterization of the motion or any other quantity. So it can be any scalar quantity like temperature, velocity, etc. Sorry, scalar or vector, any quantity like temperature and velocity vector. So with respect to the material coordinates, so if we describe some quantity, which is, let us say, phi, with respect to the material coordinates and time t, so that description will be called as the material description or the Lagrangian description. So phi can be any other quantity like temperature, velocity, etc., and this x denotes the motion. So this motion will be a function of the material point x, the initial position, and t, and that mapping. So in the earlier picture you have seen there is a mapping sign shown here. So from this to this mapping is termed as chi. So chi is the map from reference configuration to the current configuration. So this chi denotes the map from reference to the current configuration, and this is actually describing the motion, and in material description this motion is as a function of the material coordinates capital X1, X2, X3 and the time t. So here the focus is on the particle, on paid to a particle. So in the material description the attention is to a particle, and we see what happens to the particle as it moves. So in spatial configuration, or the other name of that is Eulerian description. So in that description, the motion here or any other quantity is characterized with respect to the spatial coordinates x1, x2, x3 and time t. So here the phi, which can be temperature, velocity, anything else, will be expressed as a function of the current position or the spatial coordinates x1, x2, x3 and t, that is small x1, x2, x3. Okay, so this is nothing but if we consider motion here, so that is the inverse map which is described in this way. So the motion or the position of a particle will be described as a function of the spatial coordinate small x1, x2, x3 and time t. So here the attention is paid to a point in space. So we have a fixed position in the space, and then we see what happens to particles which take position at that particular point, at time changes. So to give uh, one example of uh, some example where you can understand this to description. So let us consider like you are actually traveling in a car, and let us say that car is uh, having some uh, number plate, and that number plate will be a fixed number plate. And let us say somebody or maybe a traffic police is tracing your car and seeing what is happening to your car. So whether it is like how fast it is moving, how which path it is taking, when it is accelerating, when it is decelerating, etc. So that means your focus is onto a single car, which is a specific nameplate. And this description will be termed as material description or Lagrangian description. So here your focus is to a single particle. Whereas if you let us see if you're the same traffic police and you're standing in a traffic signal, and then you're just seeing how different cars are actually passing that traffic signal, and you are recording like when they're speeding, when they're stopping, when they're uh, decelerating, accelerating, etc. So you are actually focusing to a particular position and then seeing what is happening to a different uh, car, how their position, velocities, acceleration are changing with respect to time. All right, so this will be your spatial description or Eulerian description. So now let us see or uh, see what happens in fluid mechanics and solid mechanics. So in fluid mechanics, we never know like where from the fluid particles are coming. Let us say you are doing some experiment and there is a pipe and you are trying to measure pressure or velocity. Then you can take a particular point within the pipe and then give a pressure gauge, a pitot tube or something, and you will measure the velocity of the particles which are actually moving through that particular point. So the focus is on the position or spatial coordinate, not the material points. The fluid particles can come from anywhere else, from any reservoir, and then we are not focusing on uh, particular material points. So your focus is on position. So this in fluid mechanics, that's why the spatial description is often used. So here your focus is on the control volume, not on the particles. But in solid mechanics, because we actually know what is the undeformed shape of a uh, structure, so your undeformed configuration is known. Now we can see what is happening as the structure deforms. So here you know the position of all the material points within the structure. So your focus is on the material points. So that's why in solid mechanics mostly we have the Lagrangian description or the material description followed. Okay. And now let me discuss the displacement field, how it can be defined. So in material description, we define displacement field as u capital xt equal to the current position minus the initial position. So if you see this picture, which is for the displacement field, so this is your current configuration, sorry, this is your reference configuration, and this is your current configuration, and a particle which was here moved to this position. So this is your displacement, and this displacement is nothing but this x, the final position minus your initial position of that particular point. So small x minus capital X. So now in the material description, everything will be described in terms of the material coordinates. So the new position x, which is the small x, is also described in terms of the material coordinates capital X and T. So whereas in the special description, so the displacement field will be described again as the small x minus capital X, but here everything will be described using the special coordinate small x. So here you can see the small x is as it is, and then the capital X will be described as or in terms of small x. So these two are the same displacement field. So that means this capital U and small u will have the same values because that did represent the same vector, but they actually represent function of different arguments only. So one is a function of capital X and T, another will be function of small x and T. So we'll clear if you have some doubt. So this doubt will be clear if we just go through this small example. So let us see what is asked here. So let us say the motion of a continuous body is described by a mapping function is as this. So small x equal to some mapping function which is described in the material coordinates capital X and T. So the E1 components along the E1 vector is denoted by this E2 and E3. And then we have to find the displacement field capital U and small u. So here let us first discuss what is capital U. Okay, so there is a bracket missing here. So capital U will be nothing but the final position minus initial position, and what is the final position will be described in terms of capital X, and which is already given. So just you put those values what is given, and then you subtract from those description of position vector small x, that we subtract capital X, and that final expression is your displacement field in terms of the material points in material description. Now for the special description, we'll have the same mapping function or the motion description, but you have to express everything in terms of the special coordinates. So to do that, so this is what we have to do. We have small x, which is the present position, and minus the initial position, but that initial position now you have to describe in the special coordinates. So that you can do from this relation. So we know that from the mapping function or the motion description, so the first component of small x is this, the motion component of the motion in E1 direction, and then component of the motion in E2 direction is your x2, and x3 is the component of motion in third direction, E3. So from here you have to just find what is your capital X1, X2 and X3 in terms of small x and t. So you have to just solve for capital X1, X2 and X3 from these three equations. So that is done by little like mathematics here. So you can see one is very easy because x3 is just capital X3 will be small x3, and from the you have to just solve these two equations to find what is x1 and x2, capital X1 and x2 in terms of small x1 and x2. So that is done by just simple mathematics. You can follow this and you can see capital X1 will be expressed as this, and this capital X2 will be as this by just simple solving these two equations. And then your uh, displacement field or vector in the special description will be this as we defined earlier, small x minus capital X in terms of small x, and then you just put those capital X values. So this is your special description. Here you can see everything in terms of small x and t. So they are the same vector represented in different description. One is material description, another is special description. Now we'll define what is deformation gradient. Deformation gradient tensor. So this the deformation gradient tensor is defined in this way. The relationship of a material line Tx before deformation, and that's why it is capital Dx, D capital X, and the relationship of that D capital X to the line element D small x, which is after deformation, is provided by this deformation gradient tensor F. So deformation gradient tensor F actually relates the line element D capital X before deformation to the line element D small x after deformation. So let us see what it is by seeing this figure here. So let us say in the reference configuration there are 2 points, the closed points P and Q, capital P and capital Q, and that line element, so describing P to Q, is denoted by D capital X. So this is a vector going from P to Q, and then after deformation this P point will take some position which is P bar or P prime sometimes we call, and then Q also will take some position in the current configuration which is denoted by Q bar or Q prime. Then this P bar and Q bar will be a line element which is denoted as D small x. So the deformation gradient tensor actually will relate this line element to this new line element D small x. So D capital X and D small x will be related using the deformation gradient tensor. So what will be, so you know these are two vectors, so one vector actually maps to another vector, and that mapping is done by the deformation gradient tensor. So mathematically we'll get the actual expression, but what is like deformation gradient, what it does, it actually when it acts on the line element d capital X, it generates the line element d small x. So it acts on d capital X. We know that tensor acts on a vector and generates another vector. So here the deformation gradient tensor acts on the line element d capital X. So that is the line element before deformation, and then generates the line element after deformation, which is d small x. So mathematically, now we'll see what is the relation. So it's a small x, x1, x2, x3, a function of capital X1, x2, and x3. And then d of x1 by chain rule will be expressed as this. dx2 and dx3 are similarly expressed. And then if you just arrange them, it can be arranged in this way. So dx1, dx2, dx3 is a column matrix which is equal to this 3 by 3 matrix times a column matrix d capital X1, d capital X2, and d capital X3. So this is the vector of the line element d small x, and the extreme right is the line element d capital X, and that inside matrix is the matrix F, which is the deformation gradient tensor. So it is the derivative of the spatial coordinates with respect to the material coordinates capital X. Okay, and this is how it is referred. So here is a linear transformation which generates a vector d small x by the action of the second order deformation gradient tensor F on the vector dx. So this is what the deformation gradient tensor does. Okay, so now we'll see what is the relation between the deformation gradient tensor and the displacement gradient tensor. Actually, we'll get again one new term here by simply using this small mathematics here. So capital U already described. So it is the x, which is described in the material coordinate system, minus capital X, and then if you rearrange the motion small x described in material description is actually capital X plus the displacement field in material description, and then from here we can find what is the relation between these two tensor, deformation gradient tensor and displacement gradient tensor in this way. So F is just a partial derivative of small x with respect to the capital X. That's what we have seen. And then if you see the small x is nothing but capital X plus U in the capital U, and then from there you will get this relation. Sorry, I have marked a bigger this thing. So yeah, this one. And now simply we get this relation as the deformation gradient tensor is actually equal to the identity tensor plus the displacement gradient tensor. Okay, so whereas the displacement gradient tensor is defined as this. So it is the partial derivative of u's u1, u2, u3 with respect to capital X1, x2, and x3 arranged in this way. Okay, so this is known as the displacement gradient tensor. Now we'll define what is green strain tensor. So again, we can refer to that same picture which we have already shown, denoting these two line element P, capital P and Q, and then P prime, Q prime, or P bar Q prime. Now if we try to see what is happening to the length of this line elements, and then we'll actually from there we can get a definition of this green strain tensor. So the distance PQ, and actually the square of the distance, if I just try to calculate, so it is d capital S square equal to, we know the square of the amplitude, so square of the magnitude of a vector is the dot product to itself, so that is d capital X dot d capital X, which is this one. Finally it is the square of the components added, sum of the square of the components. Okay, so similarly p prime q prime, which is d small s square, equal to the dot product with itself, so dx dot with dx, which is again this. So now the green strain tensor will be defined in the following way. So here if I try to calculate the change of the squared length, so change in squared length of these two line elements when it deforms from the reference configuration to the current configuration, then this change of squared length will be denoted as this. So ds, so that is the new length squared subtracted by the actual or the undeformed length square, equal to this dot product minus this dot product. Now in matrix form we know that this dot product is the transpose of the matrix column vector to the column vector, and then again the transpose dx transpose dx, and then we know that dx is f dx, so then f dx transpose times f dx minus dx transpose dx, and then this transpose, if we just this transpose of two matrices done in this way. So finally if we rearrange, you will get this dx transpose f, then f transpose m minus I within the bracket times dx. So then this bracketed term, if I just denote as capital E, and this is, remember this is actually a matrix 3 by 3, so this is capital E, and this 2 is we have placed this 2 to relate this definition to the engineering strain definition. So if we discuss later, like from the green strain tensor definition, if we try to relate the engineering strain definition, then if we introduce this 2, then it will directly we will get a relation, equivalent relation easily. So that's why this 2 factor is introduced. So now you can see this E, which is equal to half of this F transpose F minus identity matrix, is denoted as the green strain tensor. Okay, so we get this relation from the change of squared of the line elements. Okay, and this is nothing but half times F transpose F minus I, and you see that by definition this is a symmetric matrix and symmetric symmetric tensor, because F transpose F is always a symmetric irrespective of what F is. And then F is denoted as I plus gradient of U, the displacement gradient. So if we just put that relation, then if you will get this strain tensor E with respect to the displacement gradient tensor grad U. Okay, and it is you can see this is the final relation of the green strain tensor. So it is a symmetric by definition second order tensor, which is called as green strain strain tensor, but sometimes simply it is called Green strain tensor, because Green has proposed this. And then mm, because of this third term, you can see there is gradient u plus gradient u transpose, plus there is actually some multiplication, and this is actually a nonlinear term. So this nonlinear term actually gives this relation as a nonlinear strain displacement relation. Okay, so the strain is a nonlinear function of the displacements u. Okay, and in index form, this vectorial vector or tensor equation will have an equivalent index form, which is denoted as this. And if we expand, then we'll get all these components. So you can see there are some squares of u's, or maybe there will be for the e1 to the off diagonal terms. So these are actually diagonal terms. They are called normal strains, and these are off diagonal terms. They're called uh, shear strains. Okay, and here also this first two are the linear terms, and these second third three terms will be nonlinear. Okay, all right, so now this is the definition of Green strain tensor, and this is actually a non-linear strain displacement relation. Now, if we get a situation where, let us say, this displacement gradients are small, that means the grad u is very, very small compared to unity, then in this green strain tensor definition, we can neglect this nonlinear terms. So that means uh, the third terms in that green strain tensor definition will be neglected. So as the displacement gradient small, that means we actually the deformation also is small. So here in this definition of infinitesimal strain tensor, there won't be no distinction between the material coordinates and spatial coordinates, because they almost take the same position, because the deformation is small, so the material point is not moving far. So the small x and the capital X are actually can be interchangeable. Okay, so this infinitesimal strain tensor is denoted by epsilon, which is half times gradient u plus gradient u transpose, and this is also a symmetric tensor by definition. Transpose of a matrix plus that matrix is always a symmetric matrix, and the component forms will be denoted by this. And now you can see every capitals U and capital X, they will be replaced in this definition of infinitesimal strains by the small u and small x, because there won't be any distinction between this uh, descriptions, because this deformation is small. Deformation is actually assumed small, so these material description and spatial descriptions, capital X and small x, can be interchangeable for this infinitesimal strain cell case. Okay, so in expanded form, this will be the definition of normal strain components: epsilon 1 1, epsilon 2 2, and epsilon 3 3. They exactly actually the matches with the engineering strain definition, which you might have encountered in your mechanics course. And this will be the shear strain components. Okay, and these shear strain components are actually half of the engineering strain. So the engineering strains which are defined by gamma actually is twice of this tensorial strain definition. So gamma 1 2 or xy is equal to 2 times the epsilon 1 2 or epsilon xy. So this has to be noted because we get a lot of confusion in the later stage. So if we have a tensorial definition of epsilon, which is the infinitesimal strain tensor, that is a tensorial strain, and those tensorial strain components are related using the engineering strain definition this way. So not for normal strains, they are actually same, nothing changes. For the shear strains, the engineering strains gamma are actually twice of the tensorial strains epsilon. Okay, so with this, let me stop for this lecture. In the next lecture, I'll discuss few more interesting uh, concept of these strains. So let us wait for the next lecture.